Okay, hi everyone. So I'm Vincent Ménoret from iXblue, and I work in the team in charge of developing the AQG, the absolute quantum gravimeter. And if it's okay with everyone, Tom's presentation will follow mine, and then we can take questions on both presentations at the end. We thought it would make sense to have it like that because my presentation is basically going to be a comprehensive introduction to Tom's discussion on the data. As a very quick forward, I just want to say for those who used to know us as Mucans that we're now part of a larger French company called iXblue, and this is why you might see the name changing on the presentations and in various documents that you might see. Okay, so what I'm going to talk today is about the absolute quantum gravimeter in the frame of the Newton G project. And as far as the AQG is concerned, the main targets of the project were to go from the first version of the AQG, which was an indoor version, to one that was compatible with use in the field. And of course, to adapt it to the specific constraints of Mount Etna, because it's, well, on some aspects, it's different to other field locations we might want to use the instrument on. And then finally is to build the instrument and install it on the volcano and operate it and see if the data was of suitable quality for geophysical analysis. So these are basically the points I'm going to discuss here, and Tom will, of course, discuss the data more into detail. So I'll just say a quick word about how the AQG works for those who might not be familiar with this. Not sure if I can point, okay. So this is a sketch of the AQG sequence. So the measurement is not a continuous measurement. It's running in a sequence which we repeat over and over again. So we have a vacuum chamber, which is like drawn here. The first step of the sequence is to trap a cloud of atoms with a laser beam, which is coming from the bottom of the chamber, and to cool them into a small cloud of gas. And in this cloud of gas, we have roughly 1 million atoms with a kinetic temperature of roughly 1 microkelvin. This is very cold, and what's especially of interest for us, it means that the atoms are actually very slow. And so once we turn off the laser beam, we have basically a ball of atoms that is very slowly expanding, and that will be the raw material to measure the free fall. So a way you can see it is that cooling the atom enables us to have a very bright source, a very collimated source, which is well defined in position and in initial velocity, and to perform the measurement. And so once the beams are turned off, the atoms are in a perfect free fall. There is no residual pressure in the vacuum chamber, so there is no drag, for example. The magnetic environment is also very well controlled, and so the free fall is as perfect as it can be. And during the fall, we apply a sequence of laser pulses, which we call a matter wave interferometer, and this is where we can derive the acceleration sensitivity of the instrument. And once the atoms reach the bottom of the chamber, and this is step number 4 here, we turn the laser on again, and we collect fluorescence from the atoms on a set of photodiodes, which are installed on viewports at the bottom of the chamber. And this is the step where we can actually read out the acceleration information that was encoded into the atoms. So the whole sequence lasts for about half a second. Basically, the trapping part takes about 250 milliseconds, and then the free fall, and during which we perform the atom interferometer, is 120 milliseconds, and the detection is like 20 milliseconds, and then we have a few dead times for settling all the lasers and so on. So we repeat the sequence over and over again, and we apply a servo loop on the laser parameters. And from the correction we have to apply at each cycle, we can derive the value of G. And so basically we get a near continuous reading of G with a sample rate of almost 2 points per second. So this is the theoretical like overview of how the instrument works. And now I'm going to explain how it's done from a more practical point of view. The main features of the AQG, well, basically the main challenge, and that's what drives the main features, was making the instrument compact to be operable in the field. And the challenge, you can have an idea of how big it was from the pictures on the bottom, which are basically 3 generations of atomic gravimeters. So they're 3 experiments that are basically doing the same thing. The first on the left is from a picture from the experiment in Berkeley, which I think dates from 2010. And you see that the laser set up to cool down the atoms and to do the interferometer is very big. So it's a very big optical tables with tens or hundreds of optical elements, which of course is completely incompatible with utilization on the field. There have been several technical developments to improve this, and you can see an intermediate step in the middle. This is the gravimeter from Hélène Sirt in Paris, which is probably one of the reference instruments in the world today. And the instrument is still quite big, but it's much more compact, and it's actually possible to transport this instrument. And you have the cylinder here in the center is where the atoms are trapped, where you have the vacuum chamber, and the optical table has been put inside a box in the background here. And then the work we did at MUCONS was making this even more compact so that it could be easily transported. The way we did this is to go from free space optics, like you can see on the left, to fiber optics. And this makes the system much more compact and also very robust because the fibers can't be misaligned, for example, because of vibration or temperature. And so this is what makes the instrument quite small and very robust with respect to external environment. And another important thing is that usually cold atom gravimeters would require many laser beams in the chamber to perform all the steps which I described previously. And here we have a specific retroreflector which enables us to do all the operation with one laser beam. And so this means that we only have one optical fiber going from the laser system to the sensor head. And this also highly contributes to the capacity of the instrument. On top of that, so this is for the hardware, but we have also put a lot of effort into the software to transform a lab experiment with hundreds or maybe thousands of parameters into a user-friendly instrument where the end user can easily understand what's going on and doesn't have to figure out if all the hidden parameters are going well or not. So this is also something that's been required quite a lot of work. And also an important point is we've tried to make it as maintenance-free as we can, especially in provision of operation in areas which are difficult to access. And I think Mount Etna is a good example, as we'll see in a couple of slides. So as I said in the introduction, one of the challenges of the Newton G projects was going from what we call the AQG-A, which is pictured on the top left here, which was the first generation instruments designed to be operated in a lab, or at least in indoors and with a well-controlled environment, especially in terms of temperature, to the AQG-B, which is a field version and to be operated in harsh environments, and especially on a volcano. So you can see from the picture on the bottom right that we've put some effort into the packaging, and so all the cases and cables are now much more robust. We've divided the number of cables by a factor of maybe 4, I think, something like that. We've also made the individual cases as light as we could. The temperature range has been extended to a target of 0 to 40 degrees Celsius. And we've also increased the length of the fiber and the cables going from the laser and electronics, which are the two rectangular cases, to the sensor head, which is the cylinder on the right. And the sensor head is the part where we have the vacuum chamber and where the atoms are actually trapped and interrogated. So in the A version, the top left one, the lab version, the cable was approximately 5 meters. And in the field version, we've extended that to 15 meters, and we'll see that that was quite useful when it came to installing the instrument on Mount Etna. And so all these changes can be seen from the two pictures, but there are also some changes which are not so visible regarding the optics and the electronics, which we've made more and more compact, and we've integrated as many functions as we could on each electronics board to try and reduce the size and the overall footprint of the instrument. We also had to make some specific developments in the frame of the Newton-G project, and the main thing was dealing with ground vibrations. Because Mount Etna is quite an unusual environment with respect to what we had dealt with before, especially because of the high level of volcanic tremor in the bandwidth between like a fraction of a hertz to a few hertz. And you can see that on the plot on the bottom right here. In green is basically like a sketch of the typical noise levels in terms of power spectrum density that we can get in our lab near Bordeaux. And in blue is data recorded at PDN on Mount Etna, and you see that there is a high excess of vibration at frequencies around 1 hertz, and this is something we had to take into account specifically. To explain how we did this, I'm going to say a quick word on how we deal with vibrations on the AQG, and this is the figure on the bottom left. If we don't take any specific precaution, the reading we're going to get coming out of the AQG is gravity, but on top of that, we'll get some noise due to vibration, because when the atoms fall, they're sensitive to G, which will be the average value, but also to the higher frequency noise, which will alias into the measurement. And so in the end, the signal to noise ratio of the instrument can be hugely degraded because of ground vibrations. To deal with this, we attach an accelerometer or a seismometer directly on top of the vacuum chamber to record the acceleration as a function of time. And while the atoms are falling, we include some real-time data processing to compute the vibration contribution to the gravity measurement, and we apply a correction on the phase of the lasers. And by doing this, we can basically get rid of the contribution of vibrations on the gravity measurement. Before the Newton-G project, we used to do this with an accelerometer, but this required us to include some electronics filters, which had some cutoff just below 1 hertz, and this was not appropriate for the Newton-G project because the cutoff was very close to where we had all the vibrations from the volcano coming in. And this is why we performed some numerical simulations to understand what the limitations were. And we ended up deciding that the seismometer with a longer period would be better suited to this instrument. And so this is what we implemented on the AQG for deployment at Mount Etna, is to include a seismometer instead of a broadband accelerometer. So we integrated the instrument, and it was installed a bit more than a year ago at PDN, so the Pizzidineri Observatory, which is located quite close to the summit craters. The elevation is almost 3,000 meters, and we're only a couple of kilometers away from the craters, as you can see on the top picture. So the domes are the observatory, and you can see the craters on the left. The there is no electricity on the site, and so part of the project was to install a dedicated off-grid power supply comprising solar panels, a set of batteries, and a diesel generator. And this off-grid power supply was installed very shortly before we came with the AQG, meaning that it was not fully tested and validated before we could install the instrument. And this caused some problems, as I will show in a couple of slides. And a specific thing about the installation is the sensor head was installed in the basement of the building on a dedicated concrete pillar. But when my colleagues and the team from INGV went to install the instrument, they found out that the staircase was actually too narrow for the laser system and the electronics to go. And so luckily, with the long cable, we were able to leave the laser system and the electronics on the ground floor and just have the sensor head go in the basement and use the 15-meter cable to link the two units. And so this was, we were very happy that we decided to increase the length of the cable for this reason. And finally, I want to say a few words about the challenging conditions. As you saw from one of the previous slides, people doing cold atom gravimeters usually work in labs with a very stable environment. And I have to say that putting the AQG on Mount Etna was quite a challenge for us, both because of the tremor, but also because of the temperature changes. And you see from the picture in the winter that there is a huge difference between summer and winter. Also because there is no access, so we can't go and see the instruments whenever we want. I mean, in the summer, it's a trip that you have to plan a few days in advance. And of course, in the winter, there is no possible access. And so we were quite worried that if there was anything wrong, then we couldn't go on site and check what's going on. But still, we managed to get it there and make it work. Here is a plot. The top plot is the temperature. So it's from the installation back in August 2020, and it runs until last week, so October 21. A few things to comment on these graphs. First, you see that the temperature changes are quite significant. Altogether, we had the temperature recorded ranging from something like 7 degrees to almost 30 degrees over the course of 1 year. You can also see from the part on the left that in 2020, there is a lot of data that's missing. And this is actually not due to the AQG, but it's due to problems with the off-grid power supplies, because as I said, it was installed just before we came in and it was not settled properly. So we had several cutoffs in the supply, and which we tried to fix with the team from INGV during the fall of 2020. But unfortunately, the power supply failed. I think it was in December last year. And so we had to leave the instrument unattended for 6 months during winter. And we were pretty worried to see if it would start up again. And we're lucky enough that last May, we were able to restart it. And it's been running pretty much continuously since then. And I'll show the data in a couple of slides. Using data from the off-grid power supply, we're also able to record the power consumption of the instrument. And you can see that it's varying and that it depends on the temperature, because we have a thermal regulation in there. So depending on temperature variations, the power changes. But it's basically it's remaining within specifications. Here, the maximum we see is 600 watts, and we think that there are some other instruments using part of the power, so maybe a few tens of watts. So our target was 500 watts, and we think it's very aligned with what we had in mind. And so now coming to the performance of the instrument, I told you about dealing with vibrations. This is a spectrogram of seismic spectrogram during 4 months of 2020 in the range of a few hertz where most of the tremor is occurring. And we isolated two parts in the data, one here in green where the tremor is quite low, and one here in orange where it was high. And you can see on the vibration spectra that there is a significant increase at low frequency. But despite that, the gravity data coming out of the instrument was of good quality in both cases, in the order of 120 microgal per square root tau when the tremor was low, and slightly higher in case of high tremor. But in both cases, the data was still suitable for use in the analysis. And most of all, it was compatible with the simulations we had performed beforehand, and it also confirms that using the seismometer was the right thing to do. And so now this is what the data looks like. So on top in red, you have the raw data over a year and a half, and of course with the gap in the middle. And then we apply a set of corrections. So of course, earth tides and polar motion and atmospheric pressure, which are the usual corrections you would apply to a gravimeter. We also have tilt sensors incorporated in the sensor head, which can compensate for the deviations from vertical position. And we also correct for possible drifts of the AQG itself, namely of the onboard radio frequency source and also of the laser frequency. And we can basically use the atoms to calibrate our frequency references inside the AQG to make sure that there is no drift on gravity due to these parameters. And so by applying all these corrections, we end up with the gravity residuals, which is the data in black here at the bottom, which we can see more clearly here. And I'll let Tom comment on the data. What I just want to say is that I think that the main thing here is that, of course, we were extremely happy to see that after 6 months in the dark, the AQG was able to be turned back on again without any problems. I think this is the first time anyone's ever done that with a cold atom experiment, leaving it completely unattended and then just turning the power back on, and we're being able to resume the measurement with no measurable gap or problem in the data. You can see also now that in 2021 that the power stable is the power supply, sorry, is much more stable than it was in 2020, and we're now able to record data almost continuously. And I think that right now the measurement, the ongoing measurement, has been started in the middle of August, and so the instrument's been running 2 months without any interruptions, and there's been many eruptions during this period, and we are very happy to see some signal coming out of the instrument. And I'll now hand over to Tom to describe these signals, and I think we can take questions at the end.
Thank you, Vincent. Right, if I share my screen like so. Is that all visible for everybody? Okay. Right, so since the AQG has been installed at PDN, we now have 3 main sites, installation sites, where we are recording continuous gravity measurements. So we have Ménoret in the north, Ménoret in the south, and Ménoret in the southwest. Today, I'm going to present some results, some in-depth results for 2020, as well as some early observations for 2021. And the focus of this analysis is we're trying to consider volcanological sources of mass density changes, and we assume that these occur in this yellow shaded area beneath the summit craters. So during 2020, the AQG recorded gravity at PDN for approximately 4 months, from about the 1st of August to the 3rd of December, when the power supply unfortunately cut. And similar to the Ouija analysis that you saw before, the data from the AQG, these are compared with data with our 2 iGravs in order to kind of assess how it is performing. We have 2 time series here. So in the top right, we have our signal from Peak Ménoret, and in this case, we are comparing it with our signal from Ménoret. These signals have been averaged over 10 minutes, 1 hour, 5 hours for the AQG. And for Solar Nave, these have also been averaged over 10 seconds and 10 minutes. These different averaging scales are related to the different methodologies that the different instruments use to obtain our gravity value. And as Vincent discussed, these gaps in the time series Ménoret are due to our power supply issues. A very strong technique for comparing our two time series is the wavelet coherence method. And this, in this case, it's identified 2 periods of high coherence between our signal at Solar Nave and Ménoret. These occur over a period of about 4 to 5 days. The first occurs in late August to mid-September, and our second phase is during mid-October to early November. Now, in both cases, when our arrows are pointing to right, this indicates in-phase behavior, and so these changes are occurring concurrently at both our stations. So if we zoom in a bit more, so here in the top, we have our Ménoret signal and our 2 periods of high coherence, and below we can see our zoom-ins. So during the first subinterval, there are these very weak oscillations, these kind of like stepping features, here for Ménoret in black and here for Solar Nave in red. And this also occurs over a relatively constant level of gravity. I should also note, please take note of the different magnitudes and kind of the different amplitudes of these variations, where we're between -100 and 100 Newton meters squared for Ménoret, whilst we're much lower at 30 to -30 at Solar Nave. And then similarly, we can look at the same signals for our second subinterval, where we observe an overall gravity decrease. And you can see very clear correlations between our 3 signals at Ménoret, Solar Nave, and Montanola. And again, please note the differences in our amplitudes, given that as these stations are located at different distances from our potential mass sources. Now, a very simple method to derive a possible mass depth and its location is by calculating the amplitude ratio between our signals. And this is very simply calculated as the line of best fit between our 2 time series. So on the left-hand side here, we have our signals from Solar Nave and Ménoret. And during our first phase of high coherence, this is an amplitude ratio of approximately 3. And again, if we go to our second interval, the amplitude ratio of Ménoret and Solar Nave is approximately 6, whilst between Montanola and Solar Nave, it's approximately 3. And again, this is reflective of the different distances from our potential mass sources. So, and in terms of kind of bringing that to kind of what that means physically. So during these intervals, we didn't record any significant ground deformation. And this suggests that these gravity changes are indeed due to kind of subsurface mass redistributions. Assuming that the position of our gravity source lies within this 2-kilometer region beneath our summit craters, an amplitude ratio of about approximately 3 for Ménoret and Solar Nave, it's just a mass source between 2.5 and 3.5 kilometers below sea level. And likewise, for our second subinterval, we get much higher amplitude ratios, and this is indicating a much shallow mass source located between 1 and 2 kilometers BSF. It's quite important to know that these depths are consistent with what we have previously observed at Mount Etna, and as well as with kind of other methodologies involving, say, geochemistry. They also observe kind of these similar depths. So if we move forward into 2021, so the device was restarted in late May, and unfortunately we missed on some potential key phases during the winter period, but it is what it is. Nonetheless, 2021 has been an incredibly active year for Mount Etna, with many fountaining events. And this is clearly reflected in our 3 gravity series. So thankfully this time we have an almost complete signal recorded at all 3 stations during this entire interval. And kind of over the longer term, we observe three main phases of gravity decrease. So we have a phase one for between June and early July, a second phase during July and August, and a third phase recently in late September. And like with 2020, these amplitude ratios are always close to 3 and 2 respectively, and it is still indicating that there is a mass source located approximately 3 kilometers below sea level. We can look into a bit more detail still. So this is a zoom in between late August and mid-October, and we observe these very clear gravity decreases that are occurring after these large fountaining events, and of 29th of August and the 29th of September, as indicated by our yellow bars here. Which is fantastic news. In addition, there is an enormous decrease associated to the 29th of August event at Peak Scenarii, but this is not detected at the iGravs. The actual origin of this currently remains uncertain. And in addition, two other quite key features are these sharp decreases recorded on the 16th of September, which you can see is detected at all 3 stations, and another one between the 11th and the 12th of October, this yellow arrow here. And these last between about 10 and 40 hours at all 3 stations. So, so to conclude my recent presentations, the AQG-B has been successfully designed, integrated and installed and operated at Peak Scenarii. And despite the numerous challenging conditions that Vincent outlined previously, it seems to be working well, and we're seeing some good correlations. This has been a fruitful collaboration between iXblue and INGV within the framework of Newton-G. And the comparison of data with other gravimeters installed elsewhere on Mount Etna has highlighted very clear correlated anomalies in both 2020 and 2021, despite all of our power issues. This provides a field scale calibration and a very strong benchmark that the AQG-B is indeed measuring gravity variations driven by bulk mass changes located beneath the summit craters. And these results, they confirm the operational possibilities of quantum calorimetry, particularly in these harsh environments, and also opens new horizons for application of the gravity method in the field. Thank you very much. I'd like to now invite any questions for myself and Vincent.
Excellent. Thank you, both speakers. Questions? Yeah, there is some applause. And 2 hands. So Marvin, maybe you can go first, and then the second hand, I'm going to look where it is. Marvin, you are muted, I guess, because we are not hearing. No, now you are unmuted, but still.
Can you hear me now?
Yeah, now yes.
No, it's okay.
Perfect. Thanks for the presentations. Really nice results. A couple of questions, maybe first to Vincent. What is actually the plan or the changes you implemented to avoid again an upcoming issue with power during this winter? So did you put more solar panels, larger batteries, more diesel, or something else?
Yeah, this is actually with the off-grid supply. I think people from INGV have been going back and forth and trying to find the correct settings. There were several issues, but one of them was that when it was supposed to suck diesel from the tank, there was some security which was not set up properly, and so this should now be okay. And I think now we're confident that it should work through the winter, and we really hope to see some data coming in the next months.
Yeah, I keep my fingers crossed for that. And I was wondering, when you were talking about this long, really super long time of measuring without actually physically being on the site, what is your experience with the tilts? So with the actual stability of the AQG, we have seen sometimes that tilts have run away probably depending on temperature gradients and issues. I don't know. I just was curious what your experience is on this topic.
I think one of the important points here is that the AQG, we're not using any pads below the instrument. So usually these tend to sometimes damp with temperature. So we're confident that the alignment between the AQG and the basement is staying constant. We have seen, however, in the time series some variations with the tilt. I think that's something we haven't looked into detail to see if it was correlated with some ground deformation, for example. But the variation has been kept in a range which we think is acceptable compared to the variations we are seeing. But that's definitely something to be looked into.
Okay, so but if I then understood correctly, you say that using these rubber pads between the tripod feet and the pillar might get influence of temperature, but if you don't use that and you have a direct connection to the pillar itself, then it's rather vibrational sources that might cause the tilts to change.
It could be deformations within the sensor head, but then given the rigid structure, these are likely to be very small, and we haven't had any evidence of these for the time being. So, yeah.
Okay. I had another question to Tom. What is actually, did you actually with this amplitude ratio you did for comparing a time series of the different 3 gravimeters in order to localize math source changes? Did you back this up by modeling, or is this only the hypothesis drawn from the amplitude ratio calculation?
Only from the amplitude ratio calculation at this time.
Do you plan on doing some mass change modeling in that area? I mean, the yes, magnitudes might allow, even with model uncertainty, to get a further information about this judgment being correct.
Hopefully, yes. I've been experimenting with Mehdi Niku's point couple displacement model code that outputs gravity variations, and trying to see if we can link the two together a bit better to help reduce this uncertainty.
Okay, great. Thanks.
Okay, then we have questions from Roland.
Yes, thank you. My name is Roland Klees from Delft University of Technology. I have a question to Vincent regarding the slide where he showed this non-measurable gap after interruption of the operation due to lack of power supply. It was a couple of months. When I remember correctly, the gap was about 10 microgal. So for someone who is used to operate the FG5 in the field, he would be very nervous to see when he revisits a site, he has a jump of 10 microgal. My question is, did you look into the origin of this 10 microgal jump? Is it instrumental, or may it be caused by temporal gravity variations? And this comparison should be possible when you look at the superconducting gravimeter record.
Yes, so we did a quick analysis, and indeed, if you correct the data using the iGraphs, then I think the gap, correct me Tom if I'm wrong, but is consistent with 0. But I don't know what exactly the uncertainty on this would be, but there was indeed some gravity change during the winter, and it came back almost at the same level, I think.
Yes, I'd like to add one of the key noise considerations at Mount Etna is a very strong hydrological signal. So particularly during, say, the month of October, when it does rain a lot, and with the snow as well, we see these marked gravity decreases. And hypothetically, the long-term decreases that we see over the year, we associate with the drainage of the system. So
okay, you are pretty sure that it's non-instrumental?
Yes and no.
Okay, it's a very diplomatic answer.
Maybe I can. I'm not sure we can say it's non-instrumental at the level of 1 or 2 microgal. I think the uncertainty would be too high, because the iGraphs are too far to have a result at this precision. Something I do want to emphasize is that what's different with the case where you would like to revisit stations on a periodic basis is that between the visits on the station, the instrument would normally not be left completely powered off and unattended. And here we were concerned, for example, that the vacuum would be all right for 6 months, which usually we tend to design the off period for more like 1 month or a few weeks. And so in this sense, we were pretty relieved that there was no like a major issue with the instrument.
Okay, thanks a lot. I'm allowed to ask another question?
Yes, go ahead, because we have time.
Thank you. The other one is more from a practical point of view and maybe not directly related to your experiences on the Etna side, but can you say something about the lifetime of the laser and laser maintenance? Do you have experiences with that?
Yeah. The laser technology we used is based on optical fibers, and so it's very robust. And we now have instruments, either gravimeters, or we also provide laser systems based on the same technology for research labs. And we now have sufficient confidence in the technology that these can be operated for several years without any maintenance if everything goes right.
Okay, and maybe another question. I noticed that the sensor unit itself is pretty compact. The laser table, the electronics are maybe much larger and heavier. Are there plans to make them smaller? Do you work on that? And can you say something about the potential?
Yeah, we are working on that. And if we can make the next version more compact and the one after that even more compact, then it's clearly a goal we have. It's all a matter of not going too fast, because we find out that each time we try to implement some new features, then we have some new problems, and so we want to take some time to validate each step. But yes, we think that this is not the ultimate size, and in particular, we have some other projects where we are working with space agencies to make some space-grade laser systems, and in this frame, they want us to make them much more compact, and this will be, of course, used on the AQG once the technology is mature enough.
Thanks a lot for your answers.
Good. Then we have questions from Pavel Dittmar.
Good afternoon. I'm Pavel Dittmar from TU Delft. Let's go back to Etna. I wonder what is actions related to vertical deformations of the ground. It's known that gravity is sensitive to vertical deformations. In the worst case, it will change by 3 microgal with every change of 1 centimeter. So then is vertical deformations measured? And if yes, then how are they converted into microgals? Thank you.
Tom, maybe you want to.
So I can't answer that one, I'm afraid. Can I forward to Daniele? I think he's more suitable.
Yes. Well, for this for the variation that has been shown for 2020, as Tom said, there was no measurable deformation, at least through the GPS network. So all the changes that have been shown by Tom for 2020, the deformation was within the error bar of the vertical deformation, at least, was within the error bar of GPS instruments. For the 2021 changes, we are still analyzing the data. There are these strong correlations, as you have seen, over different time scales of sorry. So in this case, we are still analyzing the data. But for the 2020 changes that have been shown by Tom, for sure, the associated deformation, it's within the error bar.
Then we have a question for Tom from Flavio. Did you try the coherence analysis for the 2021 time series?
Not yet. So far, we've only got the visual similarity between the signal. That's the next phase of the analysis. Similarly, we'd like to do this similar technique, comparing our gravity signal with our other parameters such as deformation, to highlight these additional correlations pointed out by Pavel.
We still have time for more questions in case somebody has some. We have a question from Julian Glessel. Vincent, do you have plans to add motors to adjust the AQG tilt remotely?
This is something we can consider, yes. We've actually designed a platform which we now use in the lab for calibrations. This has only been running for a couple of months, but we find it's pretty useful. And I think it's something that we can consider putting on the AQGs. Maybe as an option. It's not clear yet what it will require in terms of additional electronics and so on. So I'm not sure if it can be fully integrated or not, but this is definitely something that can be, I think, considered.
Then we have more questions from Rene.
Yeah, I'm from the University of Delft. I have one question regarding the laser used in the quantum gravimeter. I'm measuring with the FG5, and there's a neon helium kind of laser that you have to treat it properly. What kind of laser is used in the quantum gravimeter?
So we are using fibered laser diodes that were initially designed for the telecom industry. So very narrow laser diodes that are operating at 15, 16 nanometers. And then they are frequency doubled to 780 nanometers. So in the very near infrared, which is the wavelength we need to operate on the atoms. And so this technology is very mature, and the lasers are qualified with fiber telecom standards, meaning that they have very long lifetimes, and all the components are very well qualified.
Yeah, that's this difference then with the neon helium, where you have really an optics and everything there, and leaking of helium gas out of the tube. That kind of problems. Yeah. So it extends the lifetime.
Yes.
And it lowers the maintenance.
Yes, exactly. These lasers are very robust and they require very low maintenance.
Okay. Thank you very much.
You're welcome.
From Marvin, we have more questions.
Yeah, I have a quick question to this power usage. Vincent, you showed a quick graph, and I was a little bit surprised that you said you were expecting these 500 watts as like a normal operational power consumption. I thought it was aiming more to go in the direction of like 350 or something like this. So do you are you really considering outdoor field installations unattended, where you even maybe sometimes don't have power grid infrastructure? Do you plan on, or do you see a possibility to decrease that power consumptions? Could you explain in the graph how this is related, that it sometimes drops? Do you think this is temperature dependent, depending on the climate module, or what are comments with respect to that?
Okay, so yeah, basically most of the power driven by the AQG is from the temperature control, both of the laser system and the sensor head. So the current architecture, we have a thermal control both in the sensor head and in the laser system, because we felt that was the most secure way to have the system operate and ensure robustness against external temperature changes. But so this is what's taking most of the power. If you just take the AQG without any temperature control, the power consumption is of the order of 150 watts, something like that. And then this power consumption does depend on the external temperature, because, for example, if it gets very hot, you need to extract some heat from the laser system to cool it down, and this in turn takes a lot of power on the thermoelectric coolers we have on the laser system. So this explains why the power consumption is very well correlated with the external temperature.
Mm-hmm. So there's also no real possibility to decrease this power need?
Not with the current architecture, but well, it's basically the same kind of answer as for size and weight. We know that people working on the field would like some smaller instruments with less consumption, that they can operate off a small battery and so on. So it's definitely on our plans, and going to a more compact electronics will also help to reduce the amount of power that's required to do the thermal regulation. And we're also working on the architecture of the sensor head to make it less sensitive to temperature variations instead of mechanical interfaces and so on. So it's something that's clearly on our roadmap, but it's very difficult to tell you if this is going to be in 2 years or 10 years, and probably somewhere in between.
Yeah. Okay, that's completely understandable. Thanks.
We have time for a couple more questions. If nobody has any more questions, maybe Daniele wants to announce the session in the afternoon or say something.
Yes, just a quick comment about the last question. In any case, we have to consider, for example, with respect to an iGrav, this quantum gravimeter takes 1/3 of the power. Indeed, we considered at the time when we installed the iGravs to install one at the Pizzidaneri Observatory, but indeed it was not possible because the power required by an iGrav is too high, so it was not possible. So, I mean, already compared to an iGrav, the power taken by the AQG is relatively low. And this has, in this case, allowed the installation at the Pizzidaneri Observatory with this off-grid power supply system.